Banked curves are a really cool application. We do them right at the end of the unit because they bring in some component stuff on like inclined planes, but not exactly the inclined planes we already did. They bring in circular motion because we're talking about cars going around corners. So we leave them to the end because it kind of builds nicely. This first question that I've typed here, it's a car on level ground, so it's meant to kind of review horizontal circles back from when we tackled that earlier. You can watch the solution. I'm just going to quickly put it up here. If that's the car, can't get away from gravity, so you've got gravity straight down. You've got a normal force straight up. Since it's a level curve, that's a boring case situation. The normal is exactly the same as gravity. If the car's turning to the right, it pushes the road to the left, and the road reacts and pushes the car to the right. So this is what I was calling the reaction force, which at maximum acceleration is equal to the force of friction. I'll talk you through that in the video. The solution, I just wanted to sort of remind you of that. Because it's a boring case, the normal is equal to mg, and then as we saw before when we set up Fnet equals ma, we end up with a ff equals mv squared over r, which turns into mu mg, mv squared over r. The m's cancel and we get this cool v squared equals rug that we saw before. That's the physics of a level curve. But what if we're not satisfied with that? What if we want the car to go faster? If that's all that's going on in the physics of turning, then the fastest the car can go is limited by the coefficient of friction, the mu, the 9.8, like if you're on another plane with more gravity, you could turn faster, and the r value. But if we want the car to turn faster and sharper, there's two ways to go about it. We somehow need to increase the force of friction. One way to do it, and it's another cool application, but we're not going to get to it, is to use aerodynamics. If we can somehow change the shape of the car, so look at my little diagram here, when air flows and bumps into the car and curves upward, by Newton's third law, that pushes the car downward a little bit. Any car with a tail fin at the back, as that air kind of gets deflected up off the tail fin, that creates another downward force. So if we shape the car properly, then by Newton's third law, we can create these extra down forces. These extra down forces have the effect of increasing the normal force. We're not in a boring case anymore. We've added a couple down forces, so the normal force has to be bigger to compensate. That's aerodynamics, but we're not quite ready for the math on aerodynamics in high school, so we're going to do it a different way. Instead of changing the car, we're going to change the road. If we bank the road, then, here I had a little doodle here, sorry, I'm working outside and then you can hear some background noise. If we bank the road, what happens is the normal force now is on an angle. It always has to be perpendicular to the road, so if the road's on an angle, that means the normal force is going to be on an angle. In the video that I'm going to get you to look at down below, I'll talk you through it there as well, but now it turns it into a component thing. Component of the normal force fights gravity, and another component of the normal force is sideways to that. And this component here helps the car turn. So basically, we've added another force that's towards the center of the circle. Friction will help it turn, and a component of the normal will help it turn. Banked curves get a little bit complicated. I wrote about the topic thinking that we want the car to go as fast as possible, but when we do the math on banked curves, it kind of depends on whether the car's going crazy fast or crazy slow. If a car is going around a banked curve and it's going really fast, then the inertia, then the issue is that maybe the car would drift up and outward, in which case the friction has to be downhill to help. But if we flip it, if it's a banked curve, like maybe a curve that's banked really steep, so imagine it being exaggerated. If you go around a banked curve and you're going too slow, especially if it's steep, then the danger is you might slide down the hill, and in that case friction has to be uphill to kind of keep you from falling in. So check out this video, and I'll talk about the friction in there, but basically to figure out the physics of banked curves. We start with this case where we consider a banked curve with no friction. And then we can, depending what we're doing with the question, we can figure out, based on the physics, we can figure out the speed a car could go with no friction. And then if a car is going faster than that threshold speed, then the friction has to be downhill. Or if a car is going slower than that threshold speed, the friction is going to be uphill. So that's kind of me yabbering about it. Banked curves are cool. The friction depends on whether you're going too fast or too slow, so we need to do this no friction case to figure out what that speed is that we're comparing to, whether we're faster than it or slower than it. So take a look at the video, take a look at the question there and try it on your own, and the solution's posted there as well. As always, email if you have any questions.